Okay, for this video, we're going to focus on beta decay. So first, just a quick recap of radioactivity. Nuclear radiation, basic definition of it is a process where we have an unstable nucleus emitting charged particles and energy. Now, with alpha decay versus beta decay, we have a different kind of particle that gets released, and so that's why we're going to go over both of them. What it means when an atom is unstable, we call this a radioisotope, and basically that means that the nucleus just wants to break apart, and the forces that are keeping that nucleus together just are not strong enough, and they pull the atom apart. They break apart the protons and the neutrons that are in that nucleus. So some atoms and isotopes are said to be what we call radioactive. So they emit a charged particle. That's what radioactive means. And so we call this process transmutation. We're going to look at transmutation, where it changes the element to a different element. With nuclear decay, we are going to be using isotopic notation. So you're going to have to remember how to do that. So if you recall, with isotopic notation, when we're writing an isotope, it looks like this, where we have the atomic mass at the top, and on the bottom is the atomic number, or also the number of protons. We also learned how to write this as palladium-110, remembering again that this 110 is the mass, okay? So with isotopic notation for our different types of radiation, with alpha decay, we're going to have released basically a helium atom. And so the top number here is going to be the mass, and helium has a mass of 4. And the bottom number here is going to actually be the charge, or also the number of protons. Okay? And then with beta decay, because it's an electron that's being released, there is no mass. Remember, electrons electrons have very little mass, so they don't contribute to the mass of the atom. So if an electron's being released with beta decay, then there is no change in the mass that's going to occur. Now, because an electron is released, the charge of what's released is -1, and you're going to find out that there's actually something that occurs with the protons with beta decay, and we'll talk about that in a minute. Gamma is just releasing energy, and we write that with a Greek Y type of symbol. There is no charge to that, and there is no mass to it. Okay, so with beta decay, we're going to focus on just beta decay in this video. So how is it that we release a nucleus? Well, what actually happens is that we have a neutron that is going to break down or decompose into a proton and emit an electron. So the key thing to remember here is neutrons have a mass. Well, if a neutron breaks down into a proton here, well, a proton also has a mass. So the mass is not going to change, because if I have something that has one mass and it breaks down into something else that also has one mass, the mass is not going to change. But we are going to emit an electron, and we are going to gain this proton that it decomposed into. And so if I have 10 neutrons after beta decay, I'm going to have an extra proton. So now I'm going to have 11 protons instead of the 10 protons that I had before, and it's going to break down, and I'm going to release that electron right here that has no mass, and it has a charge of -1. So let's see how this works. How does cesium-137 break down using beta decay? Well, I am going to keep the same atomic mass because because that neutron broke down into the proton. So you can see my mass does not change, but that neutron broke into a proton. So I'm gaining a proton with this process. So 56, I went from 55 protons to 56 protons, and then here's my beta decay that is released. No change in mass and a charge of -1. Now, one way to always check these problems is basically like balancing a mathematical equation. Whatever I have on the left side has to be equal to whatever I have over here on the right side. So if you look at what I've got going on here on the right side, I have a mass of 137 in the barium and 0 in the electron. 137 plus 0 is a mass of 137. Does that mass equal the mass I started with? Yes, it does. Matter can never be destroyed or created. So whatever I start with, I also have to end with at the end. So let's look at our number of protons. Well, I have 55 protons on the left-hand side in cesium, and over here on the right-hand side, I've got 56 and then -1. So that is 55, and that is equal to each other. So my protons are equal, okay? So we have the same mass because the neutron breaks down into a proton, but we gain a proton. So we are changing our element, and you can see I had to look on the periodic table to see that the element with 56 protons is barium. So with beta decay, it does have a lower ionizing power than alpha particles do. Ionizing power means the ability of the radioactive material to ionize an atom. So its ability to take that atom and turn it into a positive charge or a negative charge. And that's actually not good for your cells, okay? But beta decay does have a higher penetration power than an alpha particle does. So in order to protect yourself from beta decay, you would need something like a sheet of metal or a thick piece of wood in order to stop that penetration. So typically beta decay is going to create more damage to the outside of your body because of that, but less damage inside of your body. And the alpha particle is going to be opposite of that. So let's visualize what's happening with the example that I gave you. In the example I gave you, we started with cesium, which had an atomic mass of 137 and an atomic number, or the number of protons, of 55. So just keep in mind, maybe make yourself a note here that this is your number of protons and the top number is your atomic mass. And so what happens with the beta decay is we have the beta particle here that gets released. So I've got a little visual here that shows you that we've got a neutron, which is the white particle here, and that is breaking down into a proton. So we're gaining a proton, okay? And we are also gaining an electron, but that doesn't affect the mass at all. So we have the same mass of 137, but we gained a proton, and so we go from 55 protons to 56 protons, and so since we changed the number of protons, we change our element to barium, and we have to look on the periodic table to see what element is number 56. So I'm going to do this first problem with you, and then I want you to try the next two on your own. So on this first one, we've got strontium, which on the periodic table is number 38, so it has 38 protons. We're just doing beta decay, so right away, I'm just going to go ahead and write in, first thing, my beta decay. So I have 0 mass change, and I have a -1 for my protons. Basically, I'm going to gain a proton, and my charge of what's being released from my energy is an electron. So my atomic mass is not going to change. 0 up here plus 90 is 90. So it equals what I've got over on this side here. Now, I need whatever numbers on this side on my bottom to add up to 38. So I'm going to have to use 39, because 39 minus 1 is equal to the 38 over here on this side. So I've got to now look on my periodic table, which is number 39, which is yttrium, which is Y. for its symbol. And then I'm done. Go ahead and pause it, try the next two on your own, and then come back and check your answers with me. Here are your correct answers. Go ahead and check them. So the last kind of radiation that I'm just going to mention very briefly is gamma ray emission. This is basically just high energy that's being released, and it's high energy photons. There is no charge, there is no mass. And typically, since there is no charge and no mass, we don't really have to do a whole lot because nothing is changing with the atom. It's just a lot of energy being released. So most of the time, it will be emitted with other types of radiation. So we'll have gamma radiation as well as beta decay occurring at the same time. It does have the lowest ionizing power, so it has the least ability to take an atom and turn it into a positively charged cation or a negatively charged anion, but it does have the highest penetrating power. So that does make it still dangerous for your atoms because it will break down those atoms, ionize them. So it does require several inches of lead shielding. It is a very high energy radiation, and being exposed to something with so much high energy will cause, even with the lowest ionizing power, it will cause those atoms to ionize. So here's what a nuclear reaction with gamma decay would look like. The product has the same nucleus because it's just emitting energy and it's just in a lower energy state. So you can see here I've got cobalt. It has a mass of 60 and an atomic number of 27. Here is my gamma rays being released, and my atom right here, my isotope, is still the same. Now the M that you see written in there, that's just telling us that it's an unstable atom, and so it can release a lot of energy. Go ahead and try writing out these two problems in nuclear decay for yourself, and then come back and check with me. So this is what your result should have been. You started with BK249, berkelium, and so here's my atomic mass. The atomic number I had to look on the periodic table, which is 97. I'm breaking down this in beta decay, so here's my beta decay right here, 0, -1 with an electron. So my mass is not changing, still 249, and I'm gaining a proton, because remember with beta decay, we have a neutron breaking down into a proton and an electron. And so we can always check our work, making sure that matter is never created or destroyed. 98 minus 1 is 97, which is equal to what I started with. With alpha decay, we're going to release a 4,2 helium. So I'm starting with my radon, which on the periodic table I have to look up is 88. The atomic mass is 224. I put down my alpha decay right there, and that means that I lose 2 protons and I lose a mass of 4. When I look on the periodic table, number 86 is Rn. Check your answers. So I'm going to finish with showing you how this radioactive decay actually works, because it's not just that the atom decays one time. It's going to keep on decaying until it's broken down all the way down to a stable nucleus. And so you can see that I have here uranium-238 and its nuclear decay. And so what happens is it releases all kinds of energy. It releases alpha decay, beta, alpha. And then over here I have written down how many years or how many minutes it takes for all of this decay to occur. So throughout the entire time, this atom is releasing lots of energy that causes ionization, which means it will change atoms into ions, which can be very dangerous for cells, which is why you don't want to be around a whole lot of radioactive decay. So take a minute, pause this video, just look at how the entire series works, because it's not just going to be one equation, it's an entire series of decay that occurs. So the last thing to talk about is radioactive decay. And so we need to define what half-life is. And half-life is how long it takes for half of the parent nucleides to decay into daughter nuclides. So let's say that I have 10 grams of a radioactive material, and the half-life of that radioactive material is 5 days. Okay? So after 5 days, I'm no longer going to have 10 grams of that parent material left. It's going to decay into the daughter nucleotide. So if it does alpha decay, it's going to change its atomic number by 2. It's going to have 2 less protons. So in 5 days, I would be down to 5 grams of this parent highly radioactive material. Now remember, a lot of times we got to go through a whole series in order to get to be not harmful, but this is just the first step. So after 5 days, I'd be down to 5 grams. Well, after 10 days, I would have half that amount now again, and so I'd have 2.5 grams. And then after 15 days, I would have 1.25 grams, and I would continue going. So see if you can figure out how much would you have left after 20 days. So it would be half of this. How much would you have left after 25 days?